Hi, I'm Simon Thompson from the Marlowe team, and we're here this afternoon to give you an introduction to Marlowe. Let's get started. So Marlowe is a special purpose language for writing financial contracts on Cardano. Now, why do we build special purpose languages, or sometimes we call them domain specific languages? Well, one reason is that we want to build languages that are closer to the language of the user and not so much the language of the system. So they're designed to be in the specific domain of the application. So a financial language will talk about payments, for example. And when we write a special purpose language, we get some advantages. We can write down things in that domain, but we can't perhaps write as much as we could in a general purpose language. And if we do work in this more specialized context, we have the advantage of being able to give people better feedback, better error messages, but also we can give more guarantees on program behavior. And that's one of the things I'm going to stress in this lecture. Okay, what sort of assurance can we give? I mean, we can give two kinds of assurance, really. We can make sure that contracts do what they're supposed to do, great, but we can also make sure they don't do what they shouldn't. And we'll see both aspects of that as we go along. We've designed the language to be as simple as it can be, and the implementation reflects that. I'll talk a bit about that in some more detail later on. Contracts are nice and readable, and also we can easily simulate them. And so we can present to users a very clear picture about how their contracts in Marlowe will behave. And in fact, we can do more than that. Because they're particularly restricted, we can, before a contract is executed, actually explore every possible behavior path it can take. So we can give complete guarantees about how a contract will behave, not just on one or two tests, but on every possible execution sequence. And also it's more straightforward to actually write mathematical proofs of various kinds of safety. So that's, if you like, the strongest criterion that we can hit in this kind of world, that we have a mathematical proof that the system will do certain things, won't do others. Okay, but let's start by asking the question, what does a financial contract do? And let's step back from what we see so what can a contract do? Well, let's take a look at what various things a contract can engage in. It can accept payments from participants in the contract. And according to choices perhaps made by one of the participants, it can evolve in different directions. Do I sell or do I stick with the contract, for example? Or it can make decisions based on external information, such as the information coming from an exchange, a stock exchange or a currency exchange, for example. So information coming from an oracle can determine the future behavior of a contract. And finally, the contract can also make payments out. If money has been deposited in the contract, it can also make payments out to participants. So we have payments, flows of money, we have choices according to external factors. And one final thing that we have, that the roles in a contract are themselves things that can be owned. So we represent that in Cardano, in Marlowe, by minting tokens that represent those roles. Now, that means that we can use those tokens as evidence that somebody is meant to be playing a role. So they're a form of security, of validation that the person submitting a particular transaction is meant to be able to submit that transaction. It fits with their role. But also it means that these roles can become themselves tradable. So we can trade roles in a running contract. I could transfer a role in a contract that I have to you, perhaps for some money, or indeed that role could be that token could be traded by another Marlowe contract or a Plutus contract. So we use native tokens to represent roles in contracts. So we have roles, we have payments, we have external choices, external information coming in through oracles. So those are the general ingredients. Now let's think about how to design a language based on those ingredients. And remember, when we design a language of contracts, what we're really doing is designing a programming language. A contract is just a smart contract, is just a program running on a blockchain. So a contract in principle could run forever. And also more subtly, it could, for example, just get stuck waiting for an input forever. If it's waiting for me to make a choice, it could potentially wait forever. It could also, as a program holding assets, it could terminate holding on to those assets. So it could lock up those assets forever. And potentially it could double spend, I guess. In principle, a program could try and do that. So there's a whole lot of security issues that a program might have, a contract might have. So what we chose to do was design for safety. So we designed, first of all, for contracts to be finite. Their life will be finite. There is no recursion or loops in Marlowe. We'll come back to that a bit later on when we talk about Marlowe being embedded in other languages. But Marlowe contracts themselves are finite. Moreover, we can be sure that contracts will terminate, and we do that by putting timeouts on every external action. Every choice or deposit of money into the contract comes with a deadline, comes with a timeout. And so Marlowe contracts cannot wait forever for somebody to make a choice, for an action to happen. If you hit the timeout, then an alternative course is taken. And reading from a contract, because we have these timeouts in the contract, each Marlowe contract will have a defined lifetime. We can read that off from the timeouts. So we have a very clear constraint on what we can do, but that gives us safety built in. And finally, we've designed the semantics of the language so that when a contract reaches its close at the end of its lifetime, any money left in the contract will be refunded to participants. So we've built into the semantics, into the way the language is defined, that no money is retained when things terminate. So we've got those safety properties. Your money is always only going to be committed for a finite length of time. It will always, if money is not spent by the contract, it will be returned to its rightful owner. Now, conservation of value is something that we get really for free from the underlying blockchain. We can't, the underlying blockchain guarantees double spend, and because we're using the transaction mechanisms of the underlying blockchain, we can be sure that we are getting conservation of value. Okay, so that's giving us a whole lot of guarantees just out of the box. And these are not guarantees that there are for Plutus contracts in general. In general, a Plutus contract could go on forever, it need not terminate, and it could terminate with having control of a whole collection of assets which are then become unreachable. Okay, so those, just to stress, these properties I'm highlighting here are safety properties, are assurances that we can give to Marlowe users. Now, what does the language look like? Let's cut to the chase. So Marlowe is, at heart, it's represented as a Haskell data type. And you can think of, I'm sure you're familiar with data types in Haskell. Data types in Haskell we can think of as syntax of simple languages. And let me just talk you through the constructs that we have in the language. We have a pay construct, and in that, a party, one of the parties in the contract, makes a payment to a payee of a particular value, and then the contract continues with what we call the continuation contract. We can go in two separate directions. We can observe whether or not a particular observation is true or not. If the observation is true, we follow the first contract. If the observation is false, we follow the second. So simple payment and then a simple conditional. The most complex construct in Marlowe is the when construct, and you can see it takes three arguments, and the first of those is a list of action contract pairs, a list of cases. And let's look at what that list represents. Let's think what it represents. What the when construct does is wait for one of a number of actions, and when one of those actions happens, it performs the corresponding contract. So it could be waiting for a deposit, which if I have a case where the first part of the case pair is a deposit, then we will execute the corresponding second part. Similarly with making a choice. Similarly with getting a value from an oracle. So here we're waiting for external actions, and of course the contract can't make those actions happen. A contract can't force somebody to make a choice. It can't force somebody to make a deposit. But what we can do is say, well, if none of these actions takes place, no action taken place, no corresponding contract, we will hit the timeout. And when we hit the timeout, what we'll do is perform this contract. So we can guarantee that something will happen in this construct, either because one of the actions triggering a successor contract, or we simply hit the timeout and go to that continuation. So we know by the time we hit the timeout, something will have happened. We can't sit there waiting forever. And then finally we have the close, which has the semantics defined so that nothing is retained when we close. So there is the Marlowe language, a very simple set of constructs, but we'll see that we can use those in a variety of different ways, that we can construct Marlowe contracts in a variety of different ways. Okay, so there's the language. What is the Marlowe product itself? Well, what we have is a suite of things. And what I'm describing here is the overall vision for Marlowe, and I'm going to describe that and then tell you where we are with fulfilling that. So at the moment, what we have is, you might have seen, and I'm going to show you a demo shortly. We have a prototype for Marlowe Run, and that is the system through which an end user will interact with contracts running on the Cardano blockchain. So if you like, Marlowe Run is the Marlowe DApp. It's the thing that allows Marlowe contracts to be executed. We're also building a market where contracts can be uploaded, downloaded, and where we can provide various kinds of assurance about those contracts. We allow contracts to be simulated interactively, and we call that Marlowe Play, and we allow contracts to be built in various different ways, and we call that Marlowe Build. Now, in fact, what we've done at the moment is bundle those two, Marlowe Play and Build, into what we call the Marlowe Playground. So as things stand at the moment, you can, it's been available for a while, use the Marlowe Playground to simulate and construct Marlowe contracts. We're in the process of redesigning the user interface of that, the user experience, on the basis of what we've done with Marlowe Run. So we're able to build and simulate Marlowe contracts. What we're releasing very shortly is the prototype of Marlowe Run, and this is the prototype of how end users will interact with Marlowe on the blockchain. And our intention is that we'll have all these products available when running on the Cardano blockchain, when we have the full support for this on Cardano, which will involve having the Plutus application backend and wallet backend and so on working as they should. Okay. Now what I'm going to do now is just take a short break and show you a demo of what we have in Marlowe Run to give you a sense of what we can do with at the moment with giving users the experience that they will have when Marlowe is running on blockchain. This will be the app that is going to provide that experience. At the moment it's running locally. We will in a few weeks time be releasing a version that runs in a distributed fashion on a simulated blockchain, and then as we go into the end of the year, we expect to have this running for real on the Cardano blockchain itself. So let's go to the demo now. Marlowe Run runs in the browser, and what it does is provide the end user interaction with contracts running on the blockchain. For the moment, we're simulating that blockchain inside the browser, but eventually this will be the tool you'll use to run contracts for real on Cardano. Now, to interact with the contract, your wallet needs to be involved to control your signature and to control your assets. So we link up Marlowe Run with a wallet. Let's link it up with Shruti's wallet. So in this window, we see the world from Shruti's perspective. And let's open up another window and link in that window the world with Charles's perspective. And at the moment, neither of them has any contracts running. They have a blank space there. But let's start a contract up. Let's set up a zero coupon bond, which is a fancy name for a loan. And let's suppose that Shruti is making a loan to Charles. She's the investor, he's the issuer of the bond. And Charles wants to borrow 1 ADA from Shruti, and he's promised to pay back 1.1 ADA. So we've set it up, we've said who the issuer and investor are, we've said what the price and the eventual value will be, and we're now going to create the contract. In order to do that, we have to make a payment of 30 Lovelace to get the contract started. So let's pay, and we ask to approve that, and the payment goes through. And you can see now in Shruti's Marlowe Run, we've got the zero coupon bond running. But also, if you look at Charles's view of the world, it's running there too for him. Let's see what it looks like for him. We're at the first step, and it's saying it's waiting for something from the investor, who is Shruti. So let's see what's happening in her view. Yes, she's asked to make a deposit. So let's click on that to make the deposit and click to confirm with a fee of 10 Lovelace and make that deposit. And then you can see her view has changed. Now she's waiting for the issuer to pay her back. And hey ho, we look in Charles's view, which is incidentally the mobile view of Marlowe Run. He's asked to pay his 1.1 ADA. Let's make him do that now. And he'll also have to pay a 10 Lovelace transaction fee. And let's make that deposit. And you see now from both their perspectives, that loan is completed. So you can see the history of what's gone on. You can see at particular points the balances that the contract holds. And in fact, we can, if we close that, we can see the history of all the contracts that that Shruti has taken part in. So I think that pretty much covers the basics of what you get from Marlowe Run. It's a intuitive interface to a contract running on the blockchain, and you see that each participant in the contract gets their view of the contract in real time, updated from what's, in this case in the browser, but eventually what's on the blockchain. Okay, so that's given you an idea about what Marlowe Run looks like, and let's now take a look under the hood and see how it is that Marlowe will be executed on Cardano. Well, here's a diagram just to give you the context. I'm sure you understand most parts of this diagram already. We have a Cardano node on which Plutus is running, and as you know, Plutus is a dialect of Haskell, more or less. Now, Marlowe is embedded in Haskell, and Marlowe compiles, is executed using Plutus. So Marlowe sits on top of Plutus, but it's also linked to, through Marlowe Run and attachment to a wallet. You'll be able to interact with, as an end user, with a running Marlowe contract, and also it gets linked to oracles and so on, sitting out there in the real world. Now, what does it mean to execute a Marlowe contract? Again, I think this will be familiar to you from your work with Plutus, but let's just talk through precisely how it works. Executing a Marlowe contract will produce a series of transactions on the blockchain. And obviously what Plutus running on Cardano checks the validity of transactions. We have a validation function. And what's the validation function for these Marlowe transactions is a Marlowe interpreter. It checks that the transactions indeed conform to the steps of executing the Marlowe contract. And that's done using the EUTXO model. So we pass the current state of the contract and some other information through as datum. So the Marlowe interpreter uses that to ensure that the transactions that are submitted meet the criteria for the particular Marlowe contract. So that's the on-chain part. Now obviously off-chain, there's a component as well. So we have to have Marlowe Run. We'll have to build the transactions that meet the validation step on chain. And if and when the contract requires crypto assets, we will have off-chain to ensure that transactions are appropriately signed, so that we will have authorization for spending crypto assets effectively. So using Marlowe Run and an associated wallet, we construct the transactions. And we get a flow of information in both directions. Marlowe Run will submit transactions to the blockchain that then can be checked, validated by the Marlowe interpreter, which is itself a Plutus contract. It's one of the largest Plutus contracts that exists. But there's also information flow another way, because suppose that the transaction I've submitted is a deposit of money into a running contract. And suppose the contract also involves Charles Hoskinson. So my instance of Marlowe Run has submitted that transaction, but Charles has also to be notified about that. And the information flows in the other direction using the companion contract to ensure that every instance of this client, the Marlowe Run, gets informed about activity in that contract. Now Alex will talk some more about the details of the implementation, but here you're seeing an outline of how it all works. Transactions are validated online through the interpreter, but they have to be built offline, and in some cases have to be authorized. And we use, essentially, the blockchain is the central synchronization point for the distributed system that is the collection of instances of Marlowe Run that are interacting to make the contract, to execute the contract. And you saw in the demo just before that we could see in those two separate windows we were sharing information. Now that was simulating it locally, but in production, this will be information that's stored on the blockchain. Okay. Now let's talk a little bit about how the system is designed in a high level way. Here's a piece of the semantics of Marlowe, and as you can see, it's a Haskell function. We take an environment, a current state, take a contract to be executed, and based on what contract that is it a close, is it a pay, we can take some steps of computing the results of that contract. And we do that in a way that uses Haskell in a quite straightforward way to advance the contract. And what we have is that this specification in Haskell is an executable specification of the semantics. And this gives us some very nice consequences. We've got, if you like, we've got the denotational, we've got a high level description of what the semantics is, and we're doing that through something that is effectively an interpreter. So we're defining at a high level this interpreter, which is an interpreter in Haskell for Marlowe contracts. Now, one really nice thing about writing it in this sort of way is that we can be sure we cover all cases, because it's it will be obvious if we're missing some cases. Writing it as something that's an interpreter ensures that we will hit all cases we need to in describing the semantics. And also, it really helps us to understand the semantics. So this was it's a really, when you're designing a language, okay, you have an abstract idea about how you're going to, what it's going to mean, but there's nothing like having an implementation of it so you can actually run the semantics. You say, well, what would it mean if we were to add this construct? What would it mean if we were to modify the semantics in this way? Now, if you'd written it in a purely logical format, it's difficult to unscramble just from the rules as they're laid out what precisely a change in rule might mean. Here it's straightforward, we can run the semantics. So we've got this specification in Haskell, and what's even nicer is that we can reuse this semantics in a number of different ways. So in the theorem prover Isabelle, we can use the semantics for reasoning and proof, and we use pretty much the same semantics because Isabelle uses a functional language as its subject. We can run the semantics in Plutus. It was written in Haskell initially, but Plutus is more or less Haskell. Perhaps not with all the libraries, but we can, in principle at least, build our implementation on blockchain from our semantics. And also we can translate the semantics into pure script for simulation in the browser. Now, pure script is not exactly the same as Haskell. Isabelle's language is not exactly the same as Haskell. How can we be sure that all these versions are the same? Well, one way of doing it is to extract Haskell code from Isabelle and test the original against this extracted code, and we do that on random contracts, and that gives us a pretty high level of assurance that the two are the same. And down the line in our roadmap, we certainly expect to be using a Haskell in JavaScript implementation at some point to replace pure script in the front end, so we don't have to write a pure script version of the semantics. When we're doing the off-chain interpretation, building the transactions to be submitted, we can use the actual real Haskell implementation by coding it, compiling it into JavaScript and running that in Marlowe run in the client code. So building the language in Haskell has given us these consequences that though we use various different versions of the semantics, we can get a high level of assurance that these are the same. And indeed, we can, in some situations, replace things like the JavaScript by the pure script by JavaScript. Okay, so that gives us a picture about how the system is put together. Let's go to another aspect of Marlowe, which I talked about it being a special purpose language, about it being a DSL, and that promoted usability. Let me say a bit more about that. One way we promote usability is that we provide different ways of writing contracts, different ways of authoring contracts. And another way we promote usability is to allow people to explore interactively how contracts behave before they're actually run in a simulation. So let's talk about those now. Again, emphasizing these are another facet of assurance for the language. We want to write a Marlowe contract. How can we do it? Well, we can write Haskell, the Haskell Marlowe data type as text. That's one way we can do it, and that's fine. And we have an editor for that inside the playground that gives that has completion, that has holes which will support completions, will make suggestions, and so on. So we can build Marlowe contracts as pure Marlowe, but there are other routes as well. We have a visual editor for Marlowe so that you can produce Marlowe contracts visually with putting together blocks, so in a way that doesn't require you to be a confident programmer. You can start off by using the visual version as a way of learning Marlowe, as a way of engaging with it. If you are a coder, perhaps in Haskell, perhaps in JavaScript, Marlowe is embedded in Haskell and in JavaScript. So we can use facilities in Haskell, like recursion or JavaScript, to describe Marlowe contracts. So we can say in Haskell, let's, we want to do this particular pattern of behavior n times, and we can write that in Haskell. And then for a particular contract, we convert the Haskell into Marlowe. We, as it were, compile this Haskell description of a Marlowe contract into pure Marlowe. And we can also do that for JavaScript. So we have that facility. And then finally, something I'm not going to talk about anymore in this talk is that we can generate contracts from initial conditions. And we've been looking at that for the ACTA standard of financial contracts. So we generate, on the basis of the contract terms, we generate code in Marlowe. So we write functions whose output is Marlowe code. So we provide users with, as well as simply writing pure Marlowe, we provide them with a variety of different approaches, leveraging knowledge of JavaScript, for example, or leveraging a non-code based approach for describing the contracts. And also we allow people to simulate the behavior of contracts. Now this is something that you can see in the current version of the Marlowe Playground. I've taken a screenshot of that. That's something you can play with yourselves. What I would say is that we are looking at different ways of describing the results of a simulation. So at the moment we have a transaction log. You're allowed to choose an action, the next action to perform. You can perform that. You can undo the last step to take you back, and then try another path. So you can step interactively backwards and forwards through the source code, through the application of the contract. What we're looking at is changing the user interface, changing the UX for the Marlowe Playground, Marlowe Play, so that we'll use something rather more like the Marlowe Run description of a running contract, so that you'll see the steps as a series of cards like this. But that's work in progress. Okay, so we've talked about usability. What about the sort of assurance that Marlowe can give users. There are two apart from the things we've seen already. We've seen that making the system transparent, making code readable, is itself an advantage. We've seen that there's simulation to give people the ability to understand, to validate their intuition about a contract. But rather more formally, we can use the power of logic to do two things for us. We can do what's called static analysis, so we can automatically verify properties of individual contracts. So that means we can guarantee this contract will behave as it should, checking every route through the contract. And also we can do machine supported proof, so not automatic any longer, written by a user, but we can prove properties of the overall system. Let's talk about those two now. What about static analysis? Well, what static analysis allows us to do is check all execution paths through a Marlowe contract, all choices of slots for a submission of a transaction. So every possible way in which the contract might be executed, we examine. And the canonical example here is the example of whether a pay construct might fail. Is it possible a pay construct could fail? And the answer is that we use what's called an SMT solver. It's an automatic logic tool, that a powerful logic tool called Z3, is the one we use, others are available, that effectively checks all execution paths. And what it does is if the property is satisfied, that's fine. We get the result, yes, it's satisfied. If it's not satisfied, we get a counterexample. We get told, here's a way, here's a path through this contract that leads to a failed payment, a payment that can't be fulfilled. So here's an example of how it can go wrong. And that's really helpful, because it means that you can debug. If you don't, if you really want to make sure that failed payment can't happen, then this gives you a mechanism to understand and to debug how that eventuality happens, and so gives you a chance to think about how to avoid it. So very powerful and entirely push button. You push a button and you get the results. And here you can see, just again to emphasize these, here's the assurance. We can do this high level check through all execution paths. So here you see a fragment of a Marlowe contract. It's an escrow contract where the contract starts with a deposit of 450 Lovelace. And checking the analysis in the playground, we've got the result. Static analysis could not find any execution that results in any warning. So that's saying you're okay. It's not going to give you a warning whatever you do. But if we change that deposit of 450 Lovelace to a deposit of 40 and analyse, we then get this warning. We get a transaction partial payment. We're told we get to a payment where we're meant to pay 450 units of ADA, that is Lovelace, but there are only 40 available. And we get given a list of transactions that take us there. So we're able to see from that how we got to that. And the problem is that we didn't put enough money in, and then we reached a place where we needed to make a payment of 450. So it's easy for us to see that we need to either make the payment smaller or the initial deposit bigger. But it's entirely push button. So we do get that sort of assurance for free, as it were. But thinking about verification, we can do rather more than that. We can prove properties of the system once and for all. So for example, just looking on the left hand side here, we can prove that accounts, local accounts inside a Marlowe contract as it executes, we can prove from the semantics that these accounts never go negative. You can't ever overdraw an account in a Marlowe contract. And we can also prove this theorem of money preservation. We can prove that if we look at all the money that's gone into the contract so far, that's equal to the sum of two things. The amount of money that's in accounts held inside the contract, plus the amount of money that has been paid out. And that's, that gives a clear picture of money preservation. So we're able to write proofs of these very general properties of the system. Now we're also able to prove other more technical things about the system. So for example, that a close construct will never produce any warnings. So if we're analysing for warnings, we don't need to worry about close constructs. So that allows us to optimise the static analysis. And we're also able to prove that the static analysis, the way it works, which makes a number of simplifications to speed things up, is sound and complete. That means the static analysis will give us an error warning when the real contract can generate an error warning, and it won't give us an error warning if the real contract can't do that. And one thing that we haven't done, but is again on our roadmap, is we can do these sorts of proofs for individual contracts or individual contract templates too. Things that we can't necessarily prove with static analysis, we can prove by proving them by hand. So high-level assurance, we get, if you're prepared to write proofs, the system is amenable to having these proofs written about it, and they give us the highest level of assurance about how it works. So I think I've said enough for the moment about Marlowe. Where can you go to find out more? Well, there's a Marlowe GitHub repository that has the semantics and the basics about Marlowe. Quite a lot of the implementation of the tools for Marlowe are in the Plutus repository, because it has that repository as a dependency, so we include it in that repository. So that's where you can find the code itself. If you look in the IOHK online research library and search for Marlowe, you'll find a number of research papers we've written about how the system works. You'll also find an online tutorial in the Marlowe playground. And finally, Alex is going to give some more information in his presentation coming up next. So just to summarize, what we have in Marlowe is a DSL, a special purpose language for financial contracts, running on top of Plutus. And because it's a DSL, it gives us assurance. It allows us to give assurance that it's harder to give for a general purpose language. And also it allows us to orient its design around users as well as developers. And also that we get assurance of contracts behave as they should and don't do what they shouldn't. Some of that is built into the way that the language is designed. The language is simple, and therefore we get readability. We also get simulatability, and we get these stronger assurances of static analysis and verification. So, okay, thanks very much for listening, and here's the link to go and see the Marlowe Playground in action. Thanks very much.